there's another gas law called the ideal gas law, and this one's a little bit different. All the laws we've talked about up till now have involved changing conditions. And the ideal gas law talks about the relationships of pressure, volume, temperature, and moles of gas under a single set of conditions. And I could show you the math on how this is done, but you're probably not that interested in it, so I won't. But we can combine Boyle's law, Charles' law, and Avogadro's law into a single gas law, and we call that the ideal gas law. And it's right here. This is an important one. PV equals nRT. So we've seen P, V, N, and T before. We haven't seen R. R is the ideal gas constant, and that's 0.0821 liter atmospheres per mole Kelvin. Okay, so that's a really weird unit, isn't it? I'll show you in a minute where that came from. When we use the ideal gas law, we have to express all of our quantities in the same units that are in R. So what does that mean? Well, here we have liters. So that means that our volume has to be in liters. It can't be in milliliters or kiloliters or anything else. Pressure has to be in atmospheres, can't be millimeters of mercury, because the units won't cancel out. When we had changing conditions, we had two pressures. And so if they were both in the same unit, no matter what it was, that was okay. The only one we were picky about was temperature, which had to be in Kelvin. But here the pressure has to be in atmospheres, the amount has to be in moles, and again, the temperature has to be in Kelvin. So this is a table that shows the relationships between the different variables and the different gas laws. I'm just going to show you how we came up with those units for R. So if we look at, oh, and by the way, there's another law that's named, it's called Gay-Lussac's law, and that relates pressure and temperature. We didn't specifically look at that, but it's there. So if we have the ideal gas law, PV equals nRT, and we solve for R, what do we end up with? Well, we're going to solve for R. So that means we're going to divide by N and divide by T to get rid of those on that side and put them over here. So R equals pressure times volume over amount of gas. Yeah, that's wrong. That's supposed to be a T down there. It's Monday. That better? That's much better. Well, what's a common unit for pressure? Atmospheres? What's a common unit for volume? Liters. Moles is what we use for N and Kelvin. That's where those units come from. Switch the liters and the atmospheres. So R is always, at least as we'll be using it, it's always liter atmospheres per mole Kelvin, and that tells you what units you have to use. I want to show you another kind of a trick here. So there's a lot of gas laws here, and you may be thinking, do I really have to remember all of these? Well, no, you could remember one, and I'll show you how you can make all of them out of it. So if you can remember Pivnert, PV equals nRT. So pressure times volume equals moles times this constant times temperature. So if I say, well, that's condition 1, and if I divide this by PV equals nRT under a different set of conditions, that's still an equality because this part equals that part. So I'm dividing both sides by the same thing. It's like dividing one side by 4 and dividing the other side by 2 times 2, right? They look different, but they're the same. Well, what's R over R? That cancels out, right? So here you have all of them related to each other. So PV equals nRT, put subscripts on it, divide it by PV equals nRT, put a different set of subscripts on it, and now look at your problem and just cross off anything that's not changing. Because if the temperature wasn't changing, if T1 was equal to T2, even if you didn't know what it was, that would divide out, right? It would cancel. If the volume wasn't changing, the volume would cancel out. So anything that's not changing, you can just cross off, and then what you've got left is what you need. And it may not look exactly like it's stated here, but it will end up the same. So let's look at this, let's look at Charles' law. So Charles' law assumes that N and P are constant. Constant amount of gas, constant pressure. So if we look at our little scribble down here, if N and P are constant, well, that means that P1 equals P2, so those cancel out. And N1 will equal N2, those cancel out. What do we have left? We have V1 over V2 equals T1 over T2. We can rearrange that into V1 over T1 equals V2 over T2. I won't go through all the steps. But this is that. And you can get all of those this way. I don't think your book shows you how to do that. PV equals nRT divided by PV equals nRT. Cross out the things that don't change, and you have your equation. Any questions? If you want to memorize equations, you're welcome to, but I'm not big into memorizing things if I don't have to. No questions. Everybody's very quiet today. Okay, we're going to do an example with the ideal gas law. Calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin. So some of you may look at that and recognize, well, there's only one set of conditions. I don't really need to make a table. And others of you may not recognize that. If we go ahead and make a table because we're just not real confident of what we're doing here, we're just not real sure about it, if we make a table and find out we don't need it, it's not a waste of time, okay? So let's just pretend that we're just like, I'm really uncertain about this, so she said make a table. I'm going to make a table. Let's make a table. So here's our table. We have condition 1, condition 2, and then we start putting in numbers. So 0.845 moles. Well, what variable is that? P, V, N, or T? It's the amount of gas. It's moles, N. Okay, next number, 1.37 atmospheres. That's a pressure. It tells us pressure. That was nice of them. We need to extend our table here, don't we? Temperature of 315 Kelvin. How thoughtful of them. They put it in Kelvin for us. What's that? It's a temperature. It's T. We ran out of problem. So down here, there's nothing. We don't have a second pressure, volume. Well, there's no volume mentioned. We don't have a second pressure, amount of gas, or temperature. So then we need an equation that only has one P, one T, and one N in it. It's not any of those funky ones. It's the ideal gas law. It's PV equals nRT. Because there's no ones and twos. There's just one. But is this table a waste of time? No, we've pulled all those numbers out and labeled them. So that's good. So we're going to use PV equals nRT. The question asks, calculate the volume. So we need to rearrange this equation for volume. This equation is kind of nice because it does not have fractions in it. So we'll divide this side by P, and we'll divide that side by P because you have to do the same thing to both sides. You've got to be fair. Pressures cancel out on that side. So we have volume equals nRT over P. And then we put our numbers in. Okay, N is 0.845 moles. I'm going to run out of room. Okay, so I'm going to plan ahead and move it down here. So N is 0.845 moles. What's R? 0.0821. And you have to put the units in. I know it's a pain. Liter atmospheres per mole Kelvin. The temperature is 315 Kelvin. We divide that whole big mess by pressure, which is 1.37 atmospheres. So we plug everything in with the units, and then let's look at those units and make sure they're doing what they're supposed to do. So here we have moles and moles, those cancel out, and we have Kelvin and Kelvin. So we were able to cancel out everything. We've got a compound fraction here with the units. We've got a fraction in the numerator, and then we have another denominator. So that can get a little confusing sometimes. But we cleared out that top fraction. And so here we have atmospheres canceling atmospheres, and the unit that's left is liters, which is convenient because we're trying to solve for volume. So then we calculate 0.845 times 0.0821 times 315 divided by 1.37 equals. And all of my numbers have 3 significant figures. So this one should have 3 significant figures. It comes out to be 15.95 something. And I want to round to the nearest tenths place. The 5 tells me I have to round the 9 up to a 10, which bumps the 15 up to a 16. And so I'm going to write 16.0. Oh, it's not atmospheres. Liters. Any questions? Because 15.95 is closer to 16 than 15.9. You got 159.5. Okay, let me do my math again. Same thing. Okay, I do make mistakes. 0.845 times 0.0821 times 315 divided by 1.37. I get 16. Okay, so just try it again. Any other questions? It's very easy to punch numbers wrong.
What was 0.0821?
That's R, the ideal gas constant.
Oh, okay.
And that's always the same. The way proportionalities work, like when we said that volume was proportional to number of moles, that means that the volume equals some constant times the number of moles. Now, for each individual gas law, that constant's going to be different. But if you combine them all together, the constant is 0.0821. And that comes from experiment. If you're you can do multiple different things, and it always comes out that constant's 0.0821. So that's something you need to remember. Any other questions? Now, another type of problem that we can do using the ideal gas law is to calculate the molar mass of a gas. So this is another question with a twist. So it's an ideal gas law calculation and thinking about what molar mass means. So a sample of gas has a mass of 38.8 milligrams. Its volume is 224 milliliters at a temperature of 55 degrees Celsius and a pressure of 886 torr. Find the molar mass of the gas. Like, okay, what do we do with this? So it's not always obvious, even to someone who's studied stuff like this before. It doesn't just always leap out at you. Sometimes you just have to think about it a little bit and puzzle over it and figure it out. So we've got some stuff for a gas equation, but then we're trying to find the molar mass. Well, let's think, what is molar mass? Molar mass is the mass of something divided by the number of moles. So molar mass equals grams per moles, right? So if we know the mass of this gas and the number of moles, we can calculate the molar mass. Do we know either one of those? We're real close to having the grams, right? They told us that the sample is 38.8 milligrams. We could convert that to grams, couldn't we? So dimensional analysis says we put grams on the top and milligrams on the bottom, and then we reach deep into the recesses of our brains and ask ourselves, what does milli mean? 10 to the minus 3, right? Milli means 10 to the minus 3. So I'm going to put 10 to the minus 3 up here. That's hard to put into the calculator, so 1 times 10 to the minus 3. So 38.8 milligrams, the milligrams are going to cancel out, and we're going to end up with 0.0388 grams. That's just a metric conversion. So that's the mass. 0.0388 grams. We need to know the number of moles. Can we find the number of moles? Sure we can. You use the ideal gas law. So the ideal gas law says that PV equals nRT. Well, what does N equal then? We need number of moles. So we need to rearrange this. We'll divide by RT over here. So those guys cancel out. We'll divide by RT over here. So N equals PV over RT. What's the pressure? 886 torr. Is that a good unit? No, because R is liter atmospheres. So we need the pressure in atmospheres. So let's just do some little side work down here. The pressure in the problem is given as 886 torr. And we're thinking ahead a little bit. If you didn't think ahead, you could put them in And then you'd look at your units and say, that's not going to work. The units don't cancel out. And then you'd back up and do this. So I don't have room to do all that. So we need to convert this to atmospheres. And we should remember that 1 atmosphere is 760 torr. So we've got 886 times 1 divided by 760. Got an extra 0 in there. 1 point, I'm going to carry an extra digit. 1.166. This is the last significant digit. So that's the pressure. The volume was given to us in milliliters. So they were really nice to us in the previous problem and not so much in this one. What does that need to be in? What unit? Liters. Okay, so we'll multiply by liters and divide by milliliters. Oh, that's just like milligrams to grams that we just did. Milli means 10 to the minus 3. So that's 1 times 10 to the minus 3. So you can do that on your calculator, or you can do that one in your head. 0.224 liters. And the temperature they gave us was 55 degrees Celsius, and that's not the correct unit either, is it? We need that to be in Kelvin, so we have to add 273. 55 plus 273, 328. So this problem, we had to do a bunch of little unit conversions on the side. Why would we have to do that? Well, because this is a small amount of gas, and these are the sorts of things you might measure in the lab. You know, the barometer over here, 747.0 millimeters of mercury today. Well, that's the same as 747.0 torr. The barometer doesn't read in atmospheres, but we need atmospheres. The thermometer that you would use doesn't read in Kelvin, it reads in Celsius. The volume on graduated cylinders and other labware-sized glassware is usually in milliliters, and so that's why those units often come up. Now we have everything in the correct units, so we can plug these into our equation. So the pressure is 1.166 atmospheres.